The goal of this project was to determine how best to utilize a new smog-reducing technology for sustainable citywide implementation and to determine how to mitigate any problems with it. The Environmental Protection Department of the Government of Hong Kong's Special Administrative Region contracted Team 20 to analyze the smog-free tower technology. Pollution in Hong Kong is causing health problems among the population, and with pollution getting worse as days go on, a solution is needed in order to bring clean air back to cities like Hong Kong. A technology developed by Down Rosengard seems to be a possible solution, but its viability is unknown. By analyzing the solution using a numerical model, the viability can be determined. Team 20 used the Gantt chart to organize its project in order to meet all deadlines. The Gantt chart was split up into research, developing code, testing code, creating the poster, and writing the written.
In terms of our methods, we created a model that accepts as input the diameter of the particle, the voltage across the plates used for collection, the distance between these plates, and the initial distance the particle starts at. Our model yields the terminal velocity of a particular particle and whether it will be collected by the smog-reducing device within an hour, thus indirectly indicating the maximum range of the device. In order to develop this model, we identified several primary forces that would be acting on any particle in the airspace of the device. Drag force, buoyant force, the force due to other charged particles, and the force due to the plates of the device were selected as the four forces that would affect the particle we were attempting to simulate. Notably, while we originally modeled the force to the device on the particle via a calculation involving the charge density of a plate, this proved to be inaccurate as the exact charge density of a given plate was unable to be determined. Due to the challenge of manipulating the charge density of the plate, the team made the decision to switch to defining the electric field strength as a function of voltage and the distance between the plates of the device. This was far more intuitive than the first method of calculating the electric field force, and it allowed for easier analysis of the viability of the device when using values of voltage versus charge density. Once all the forces had been clarified, an equation for Newton's second law was generated and acceleration was solved for. Importantly, the calculation of acceleration was halted once it came within a close margin of zero, as this represents the point in which the drag force overcomes the other forces acting on the particle to create no net force on the particle. Some key assumptions we made include that we simulate the motion of the particle, and this is of a single particle moving perpendicular to the ground. This importantly implies that crosswinds were not taken into account when modeling the motion of the particle. Similarly, due to the negligible effects of gravity and the buoyant force on the particle, no simulations were conducted for when the particle was traveling parallel to the ground because the difference in trajectory was assumed to be minuscule between the case our model covered. What this appreciably means in the model is that the effective distance for collection of particles is represented by a radius around the device, despite the fact that we are calculating the trajectory along a single axis in the physical simulation. Additionally, it was necessary to approximate the velocity and distance traveled by the particle using Euler's method, and it was assumed that the particle traveled at a constant velocity after its initial acceleration to reach terminal velocity. The electric field due to the plate was also modeled as being infinitely large to generate uniform field lines, and the concentration of other particles in the airspace extended to the initial height and was parabolic in nature. Another application of our model included graphing the voltage between plates associated with the maximum distance of total particle collection in an hour to determine the relationship between these two concepts. This would help us tremendously when determining how to scale the system across Hong Kong to appreciably reduce the presence of particles in the air if it proved to be a viable method. While there are some limitations of the model, namely the lack of infrastructure surrounding the probability that a particle will encounter an external force that would disrupt its collection, Team 20 wanted to provide a simulation that represents the optimal working conditions in the model for reasons that will be touched upon in the discussion.
Once the model was completed, the team seek to determine which variables were the most sensitive through the Cotter's method. Of initial height, distance between the charge plates, particle diameter, and the change in voltage across the plates, the only variable with high sensitivity was the voltage difference across the plates. Somewhat surprisingly, the initial height of the particle actually had zero sensitivity because this distance negligibly affected a particle's terminal velocity. In reality, however, particle distance from the plates has a large impact on the success of particle capture. because horizontal forces such as wind will have a higher likelihood of changing the trajectory of a particle along its route to the collection system. For this reason, Figure 2's graph of voltage versus particle distance traveled in 1 hour had its y-axis labeled maximum effective height for particle capture, recognizing the model's limitations regarding wind. Following the discovery that plate voltage was the most sensitive factor, the model was redesigned to calculate this maximum effective height of particle capture over a range of voltage values. When this data was graphed, what resulted was a linear relationship between distance traveled and potential difference. The linear relationship makes sense because the time of acceleration to a particle's terminal velocity is negligibly small, and the plate force pulling the particle is equal to the particle's charge times the plate's voltage divided by the distance between the two plates. This force increases linearly as the voltage increases in a linear fashion.
To come to a final conclusion regarding the smog-free tower technology at large, the metric for success was defined to account for the outstanding pollution sustained when exceeding the potential of the solar panel currently being implemented to power the technology. The solar panel, providing 75 volts, becomes obsolete when encountering scenarios when an effect radius of more than 2.1 meters is desired, which is certainly the case for the needs of Hong Kong. As defined by the team, an effective radius of 50 meters per tower was determined to be necessary in order to meet the viability standards put forth for cleansing a metropolitan area of smog contamination. The excess voltage necessary to enable such effects from a single tower is 75,000 volts. However, due to the necessity of drawing from the fossil fuel-powered Hong Kong power grid, the net effect of such an arrangement would actually result in a net positive effect, meaning that more smog particles would be emitted to the atmosphere from the power grid than could be collected from the tower. Therefore, the team can conclude that the smog-free tower model of cleansing Hong Kong is not viable for use in the metro area at large. Furthermore, due to the assumptions already discussed, the model was set up to evaluate the best-case scenario for the tower's performance. Therefore, placing the device into a natural environment would almost surely lead to even less favorable performance than is anticipated by this analysis, further affirming the ultimate conclusion that the smog-free tower technology is not viable for Hong Kong. Thank you.